she's all over the world. Recently she was at Cornell University in US, and I've worked with her on various topics, she's expert in statistical analysis. Her mentor, she graduated from Indian Institute of Sciences and Technology in ISER, it is called, right?
Yes.
Indian
Institute of Sciences,
right. At Shivpur, and her mentor, Dr. Samantha, is very well known in, as well as her work has been quite cited work. So it's an honor to have her, and so Dr. Sardak, the podium is all yours, and whenever you want, can you see the audience here? Can you see all the participants?
Yeah, I can see.
Okay, awesome.
Yes.
And we can hear you as well. So whenever you are ready, thank you for being with us, and whenever you are ready, you can start.
Yeah, thank you, Dr. Mawai, for introducing me. Good morning, everyone. I will just share my screen, then I will start. Is it visible to everyone?
Yeah.
Okay, I can start now. So, basically, my title is Statistics in Infection Disease Epidemiology. Like, the topic is mainly covered from data to decisions. Like, we have lots of data. So, how can we implement and how can we take a decision about the policies or in real world data set, etc. So, first question is why data driven epidemiology? Why we do it in statistics? So, infectious disease processes are heterogeneous and noisy. Like different regions have different diet patterns, different cultures. So according to this, there are so many diseases that based on this variation. So purely mechanistic models really on strong assumption. Like in this model, we assume it's homogeneous, mixing, perfect reporting, fixed parameter. But in real situation, it does not happen actually. Generally, we taking the surveillance data, reveal what actually happens and not what should happen. Like, depends on under-reporting. Like someone report in delays, so we can't take decision about any particular event or any certain disease. Public health decision must be made under uncertainty. So that implies data quantify uncertainty and the risk factor. So next one is the type of data in infectious disease study. Data in epidemiology observation basically on health event and exposures. So exposures means the effect which are that is the ingredient or effect that mainly depends on the public health. Like give an example, like if you have low immunity, you have higher risk of any disease. So the population, which population we are interested, like if we take the population, our target group is children or adult or the older people. So we need to mention the which population we are targeting. Next, collected data over the. So we need to mention which region we are interested in, like the low middle income countries or the high HDI levels. So that is also important. And one of the main important factor is time. because before 2020 or before that we do not have any idea about COVID-19. But after 2020 or 2021, we saw the how it COVID-19 actually. So in the worldwide, we all know about it. So based on these, the type of data are I have divided into four categories like incidence versus prevalence, count data, rates versus proportion, time series data. So we define one by one. First, before that, we just measuring disease frequency. Why we measure disease occurrence? So the quantified disease burden in the population, like how many people are affected, how many people are improved their from particular certain disease, enables comparison across time, place and group, like which particular group are affected most, or which place are low immunity or high immunity based on the data set. Informs resource allocation and public health planning. So based on this disease, we can plan like future plan how to improve this disease or how to making any policies or we can help to the policy maker to improve the basically we want to improve the public health. So based on this, we just measure disease occurrence and distinguish between existing burden and ongoing transmission. So first definition is prevalence. Prevalence means the proportion of individuals currently infected at given time. It reflects both past infection and disease duration. Basically, the mathematical definition is prevalence equals to total population at time t that and divided by the number of existing cases at time t. So the number of existing cases, number of existing cases divided by total population. So this is an example. If 300 people have tuberculosis disease in the population is in 1 lakh, so the prevalence is it's easy to calculate. So 300 divided by 1 lakh, so it's 0.3%. Next measurement is incidence. Incidence is measure the new cases. Like we already know these like 1,000 or 300 or 500 people are affected. So in incidence is different from prevalence because it's a new cases. How many new cases have arise due for a particular time interval. So the definition of incidence is the population at risk divided by the number of new cases during the specified people. Sorry, if this definition is actually reverse, the number of new cases divided by the population at risk. Okay. So let us give an example. If 120 new cases are arises among 1 lakh people, so the incidence is 120 per 1 lakh per year. Here the key insight is prevalence is not equal to incidence because disease with long duration can have high prevalence even when incidence is declining. So prevalence is the proportion like how many people are affected divided by total number of people, and incidence is the number of new cases divided by population at risk. Next one is count data. So count data is basically like we can count the number of events. So of course it is non-negative integer starting from 0, 1, 2, 3, 4, etc. Here the number of new cases reported, maybe the number of cases reported in each day, or number of dead people due to particular disease in a week, or number of hospitalized patient, like how many people came by this week for particular certain disease. So these are the common example of the infectious disease. One of the most important example due to COVID-19 in a district, like 120 COVID-19 cases, 50 lakhs hospitalization and 3 deaths were reported in 1 week. So this is one of the example of count data. What is the key point here? Count data measure how events occur, not how large the population is. So next, next one is proportion. So proportion is a part of whole, or it can measure by numerator is included in the denominator. Does not involve the time in the case of proportion. This is the most important part of proportion. Let us give an example, like 200 individuals out of 10,000 people. So the proportion is simple calculation, 200 divided by 10,000. But in the case of rate, measure how much events occur, including time, in the denominator. Numerator is not part of denominator. So the example is 200 new infection over 1 year in a population, like the population is 10,000. So the rate is measured is always the 200 new cases divided by 10,000 person per year. So this is the basic difference between proportion and rate. That the in the proportion we does not involve the time, but in case of rate, time is one of the most important factors. So here the key message is proportion describe how much and rates describe how fast. This is the key message here. Next one is one of the most important and time series data. In time series data, the basic concept is like how many people are infected. Like give an example, like how many people are infected due to malaria or due to dengue in 1 year. So if we collected the data like 2000 year, 2001, 2002, like over time, if we collect the data over time, then it's called time series data. We can also say from its name. So the definition is here: data collected sequentially over time, observational time order. Like you can choose the time order like with 1 year gap, like 2000, data from 2000 or 2002 or 2004, like gap, or 5 year gap, like 2000, 2005, 2010, 2015, etc. Or you can take each year data set, like 2000, 2001. Each one is included in time series data. So here some examples are based on infectious disease, daily reported COVID-19 cases in a city, weekly dengue cases over 1 year, or monthly influenza deaths. So first the key point here, time series data capture how disease pattern evolve over time and requires special care due to trends seasonally and reporting delays. So time series data basically capture the time. Here the most important factor is time. In previous cases, we find that in proportion there is no mention about the time. So next is what challenges actually we face to collect the data, or after reporting the data, or to make any decision about the based on data. Basically, role of uncertainty in public health. Like decisions are made under incomplete information. Sometimes in different situation, we cannot take any decision. Like we measure, let's give an example, like we measure in a particular rare disease or in any rare cancer of a particular patient. If he or she does not follow the follow up, so we cannot conclude what happens with him or her. So in this condition, it's incomplete information. We can conclude it. Uncertainty affects risk communication. Like we measure one patient what affect the effect of COVID-19, but certainly he was died due to heart attack. So this is the uncertain effect. We can't assume this what happened with him. So we can't say that like COVID-19 how affect its progress due to death or due to mortality or not, because he was already died due to heart attack. So policy should consider ranges, not a single number. This is the important one of the important factor in role of uncertainty in public health. We can conclude like a single number. This is the result, like 1.1 or 1.2, because we can't take decision. So it's better if we provide a break or an interval. So this to this, like lower and upper interval. If we provide it, then we can take any decision after considering any target population. So this is real world data challenges. So under reporting of infections, reporting delays, right censoring, and reported cases when the cases are two infections are not equal. So based on this, under reporting of infections, like sometimes it is not possible to report exact number, like how many patients are affected or how many people are at risk. So in that cases, our decision is we can't predict the decision. Sometimes reportings are delays due to some uncircumstances reason or any like costing effect, anything. Right censoring means outcome not yet observed. Like which outcome can come, we cannot observe properly. Like maybe for any infected people, we some due to some circumstances, maybe the patient can survive up to 5 years. Maybe after 5 years, he will still survive. So we can't conclude from this situation. Sometimes the cases and the two infections are not equal. Actually, the cases we cannot maybe anticipate due to some uncertain reason. So in that cases, we can't predict how many people are actually affected, how many people are survived, or how many people have mortality or any other situation. So in these cases, we sometimes introduce in statistics the regression models in epidemics. First, we try to simple linear prediction, like we consider two axes, x-axis and y-axis. We maybe there is some linear equation y equals to a plus bx. We know the value of a and b, or we can compute the value of a and b, and we just put x and it's just y. So maybe if many people are infected, then its mortality rate is high. So this is the linear regression. It's a simple regression. The relation between x and y are linear. So it's called linear regression. we can measure trends or counts or rates, etc. But in real world, the data is not always linear. So what should we do? So it's maybe quadratic or any other polynomial polynomial regression. So some cases are there here where we can measure the probability of infection, that is based on the binary outcomes like 0, 1, effect or effect not affected, death or not death. So based exposed or non-exposed. So based on this, we introduce logistic regression, and based on this we have adjusted some co-founders. Co-founders are like from based on like the example is age or gender or etc. And we also widely use in surveillance data to use this logistic or linear regression or etc. So the challenge is sometimes the data is not fitted well, or we don't know is it linear pattern or any quadratic pattern or what. So before fitting in the model, we always plot the data. We need to plot the data before the modeling. Okay. So first it is that's why we define explanatory data analysis. Explanatory data analysis means explanatory data analysis is the process of examining and summarizing data using simple graphs, like which is visible clearly, like this data is high, this data is low, and summary measure before applying any statistical model. So before fitting any model, just visualization. Anyone can understand this graph, like this data is high, or rate is high, or rate is low, or the rate is first high then low. So we can easily interpret it from the visualization of any pattern of graph. So purpose of explanatory data analysis is understand the structure of data, like what data or what factor are included in the data, what the structure actually of the data. Detect pattern, trends or outliers. So pattern trends means the disease is gradually increases or gradually decreases. Outliers, maybe there is some outliers in the data set that is not included in the data. This is very high value. So we called it outlier in the language of statistics. So there is some formula, of course, of the outlier. So we need to rectify the outlier. These are outliers and these are included in the data. Based on there is some criteria, median or maximization. Next one is the purpose of explanatory data analysis is identify the data problem or if there is any abnormalities. Like the data consists like all the important parameters or co-founders or anything else. So here the key message is always explore and visualize the data before fitting the model. So this is the fundamental of explanatory data analysis. Never fit a model before plotting the data, and explanatory data analysis reveal the structure, bias or and anomalies. Next one is interpreting uncertainty. So if we consider any single base case from the data, like in math we call it reproduction number, or anything we consider R0 denoted by if we take any point like 1.4 or 1.6 or whatever the value is, it's better to provide in point estimation, actually in point estimation what happened, we just guess, estimate means we guess what the parameter is. So we need to guess what the parameter is based on some properties like unbiasedness, consistency, etc. This is the basic property of statistic under the point estimation. So based on these properties, we can choose the value like this is the best estimator or not. Sometimes we can't estimate in particular value, or we divided the estimation in two parts. One is point estimation and one is confidence interval. So point estimation is based on properties I have already mentioned, and in confidence interval actually uh, we measure the range of the possible values. Like this parameter is lies on like the exact value is 1.4, but we can say we can calculate the exact value. In that case, we consider the confidence interval like the value is lies between 1.1 to 1.6 or 1.5, whatever the value, in the range or in the interval. So we, of course, there is some error. So we need to consider what happens. Like we mentioned in statistics, we consider two types of interval based on like 95% and 99%. In 95% confidence interval, the error is actually 0.05. Like if there is 5% fault, okay, we consider it. And in 99%, if we consider similarly from like 1%. If there is 1% fault, then okay, we can our assumption is correct. So based on this, there is some measurement error, like exposure may be misclassified. Like from contact history, like from based on which maybe we take the wrong exposure. In that case, we can't conclude the actual situation. Outcome may be mismeasured. Maybe we can't able to catch the what is the undetected infection, leads to biased estimate. Maybe we know the person. Maybe it can happen. You know the person very he or she may be very well known. So we know the person. In that cases, or we know the disease. So we can, in that case, maybe it's the bias estimate. Maybe this person has another disease, but we cannot progress that disease. We can't detect from the copy. So the last one is confounding. Confounding is one of the main in epidemiology. A third factor that affect both the exposure also the outcome, and it can create the false or any maybe there is no relation between this and this. Maybe there is no relation between the exposure and the anything what we measure the disease. Maybe confounding make a relation. It's a very really fault. Example, age confound the link between exposure and disease severity. So we can conclude from it. So this is one of the most important factor, but it can create any false association. So what's the key message here? So here the key message is public health decision should rely the uncertainty ranges, not single numbers. So since there is lots of error due to lots of reasons, so we can't conclude it's better not conclude with particular any point, it's better to conclude within a range, like this range to this range. There is some lower, there is some upper. So lower range is maybe A and upper range is maybe B. So if the mean value is X, so it's between A less than equals to X, less than equals to B. So it's between A and B. So we called it A as an lower limit and B as upper limit, or lower interval and upper interval. So next is what happens in explanatory data analysis.
So,
Sometimes
Dr. Ghosh,
decisions
can you
are
hear me?
often
Dr. Ghosh, can you hear me?
yeah, I can hear you.
Yeah. Just let me talk to the participant a minute. So, we have to make this as an interactive session. It's very, very important. What you might be thinking is very easy. It is not. How many of you have done rates and proportions? Do you know what is the challenge in estimating rates and proportions? In reality, what is known to us? What is known to us in reality? Many times when we do the data collection process, we get proportions. We don't get rates, or vice versa. Sometimes we get rates also, but we have to convert it into the other things. And it is not easy. How do you convert from proportions to rate? How do you convert from proportion to rate, or vice versa? Note one thing, proportions are having no time units, where rates has a time units. And this type of things happens all the modeling work. How do you convert proportions to rate? Anyone? It's a very simple question, no?
Yeah, time, like in proportion, it is a part of a whole. There is no dimension rate. Proportion is dimension rate. And when we talk rate, it is time inverse.
Okay, so how do you convert it?
So time inverse, we will take time, some time staying, 1 day or weekly or monthly.
The proportion is given over a period of time, then we can calculate.
Usually, it should be a cross-sectional study, right? A cross-sectional study, there is no time. Today, I am doing a study and I am counting the number of people of certain type divided by total population. That's a proportion at this time. Today. So it's a cross-sectional. Of course, you can take over duration. You can calculate the proportion over last 1 year, which is also a cross-sectional in some sense, by the way. But it is typically one instant of time you calculate the count of your interest divided by total count. That's your proportion. And how do you calculate the rate? It has over past 1 month, past 1 week, past this thing, and you use that by averaging over many time durations. You're averaging over many time durations. You're calculating average over this time period, then over this time period, then over this time, and taking an average. That is an average rate for you. So my question comes very clearly. One is cross-sectional proportion. One is over time slots, averaged over many time slots. How do you convert proportions to rate? And this is, I'll tell you an example. For example, the models that we discuss, SIR type model, what is the parameters? But is it a rate or is it a proportion? It's a rate. Where do you use proportions? Have you used Markov models? Or have you heard about Markov models? Okay. Yeah. So that has a probability in it. Probability is typically initial simple models do not have time dependent. It's a proportion. That's how you capture the proportions in the probabilities. Okay. So my question is, that there are Markov models where you use rates also, right? So if you are given a data on proportions and you want to convert into rate, what do? You leave the problem. Any idea? It's a very simple thing I am asking. You see how tricky it is? As soon as I start asking this thing, that is what she is talking about on the slides. I'm not sure if we understood what she was mentioning. So there is a simple model is used to convert proportion to rates and vice versa. Right? So it's you take a box and you put an arrow out of the box. And let's say I represent the things in the box is X and the arrow coming out is a rate. Let's say gamma. So you have X prime, the change. So this thing is leaking out. Suppose there is a tap. It's leaking out the water and there is a water fill there. And you want to know how is X changing. So the leaking out is X prime is equal to minus gamma X, right? It's a linear equation, you can solve it. Once you solve it, you will guess X, right? You will get xt equal to, it will be an exponential solution by the way, right? So then what you do, this is xt, right? At time t, if it is leaking out every time. Then you started with x0, right? You started with x0, initial amount of the container, x. So you subtract x0 minus xt, that's what is left right now. Does that make sense? And you divide it by x0, that's a proportion. Is that making sense? At time t, you are getting proportion by taking x0 minus xt divided by x0. And the right hand side will be the rate in exponential form. Although I am just giving it in words, I can write it down if there is a board, but it's very simple, but proportion is used. So then as soon as you write x0 minus xt divided by x0, that's a proportion. And the right side is a gamma, which is a rate. So now you have a proportion of people in the compartment and the rate at which it is leaking out. So you can convert this, use this formula. You can isolate rate if you are interested in finding rate from given the proportion, or you can have a proportion in the terms of the rate. Now it's an approximation, it's not an exact answer, but this happens all the time. Simple things, and we struggle days, months of finding these estimates. So that is what she is trying to explain. There are subtle things, very subtle. She's talking about uncertainties, right? Where is the uncertainty come from? You know, I will be talking about stochastic frameworks in the very end. These are advanced models. But when we say stochasticity, what does that mean? Statistician spends whole their life evaluating uncertainty. That's their bread and butter. That's their roots analysis research. They only look at the uncertainty. So she is telling very important things in each and every sentence if you carefully listen what she's saying. Which is not obvious to a mathematician or non-statistician, I would say. Not obvious. You learn it by, people in statistics have spent they have done the degree as well, just like us did in mathematics or anthropology or biomedical sciences. We did it in our own field, right? It's a different language. So uncertainty, can you tell what is the uncertainty means? What does uncertainty means when it comes to your mind?
Randomness in any process.
But where is it coming from? That's my question.
Like in epidemiology, mathematicians use continuous model with differential equations. They do some assumptions.
Again, you are going to the methods. Just give me where is the uncertainty coming from? My simple question.
Yeah, like,
But why? Why is coming from data? If that is coming from data, and
Like
that is
in-
not the only uncertainty.
Like in data, if some epidemiological survey is done in some hospital, sometimes they are asking for age. So some people don't mention their age, sometimes they don't mention their gender. That's
Okay, well that's a missing data, but that's not an uncertainty.
Incomplete information.
Like this, a person is infected, he meets many susceptible ones. Now, it is uncertain whether he is meeting 4 guys who is getting infection and who is not getting infection. This is not
So
certain.
what you are saying is a human error. Human's error?
One is infected and I am infected from a disease, I am meeting 4 susceptible guys, they are not infected. Now it is uncertain who is getting infection from me
Okay.
and who is not.
So what type of uncertainty? There are thousands of other uncertainty. There is a categories of uncertainty. So what type of uncertainty is this? So what he's saying is the chances of person getting infection. This uncertainty is originated due to what? And each of the reason I'm coming to the point that each different type of uncertainty is modeled mathematically in a different way. That is what I am trying to come. So if you can pinpoint where is the origin of this uncertainty, then you will know which model to use. Otherwise, you are always thinking it's something with the data. What is that data? What uncertainty we are doing?
In this case, it's quite possible that it has not been reported. I am infected, I am passing it to others, but I am not going to the hospital or any medical person.
Okay.
The
So
case will not be reported.
right. So it is underreported or unreported. In that case, the uncertainty is due to underreporting. Underreporting is causing. What other things can be? Yeah.
So in general, when we define something on the basis of something, there are other factors which are influencing, which are not in our prevalence. These cause uncertainty or things.
Yeah. Well, but that is, you are saying, I don't want to worry about uncertainty and I'm clubbing everything together. That's not the way a statistician thinks. That's what I'm trying to come to the point. A statistician doesn't think this way. You are saying, oh, there is something I don't know, and therefore all of those things I club it together. And that's my uncertainty. It is done very separately. They separate it, tease it out, every source of uncertainty. And I'll come to this point that Sir was talking about. That uncertainty source, it could be that reporting error, right? So that means the patients may not be coming to the hospital. That person was infected, but did not showed up in the hospital. That's a source of an uncertainty, not showing up. Other is person has symptoms, come to the reporting, get reported, but someone noting down made a mistake, right? Third type of uncertainty is someone noting down but think, oh, he's from this region, he cannot have that type of infection, so he did a bias, personal bias. You see how different uncertainties are there? And these are very much treated very differently by statisticians. It's not like if you go deep into that, you will realize how critical these uncertainties are. And each one has a different modeling implications down the line. How you assume certain things impact your output drastically. And that's why there is a field called as statistics. Otherwise there won't be any things. What they do is capture different type of uncertainty in the empiric data, basically. That's the field called statistics. I don't know if you guys have realized that. So this is what I am trying to, and she is a statistician, so I want you guys to ask that question if something is not clear and go deep into that. She did touch many different things with a very simple way. And I think there were a lot of loaded things in that that information. So, Dr. Ghosh, you are still there, right? Can you hear me?
Yeah, sure. Thank you. Thank you.
Yeah.
Yeah, I can hear you. Yeah.
So, you know,
Thank
where
you,
is,
Dr. Mobile, for your nice explanation.
yeah, expert, you know, EDA, where do we use EDA? Have anyone used EDA? For what?
Before developing model, when we get data, we for defining clues which can be included in the model. We many types of examination we do on the data. Scatter plot, we see what of the area, which type of history we are getting.
So expert,
We can actually plot the data and sometimes we can look for the pattern. What kind of function can we fit to that particular data set?
yeah, so it's exploring the raw data without fitting, without going into sophisticated modeling. You're not, why do we, what is the purpose of the model? What is the purpose of the model?
Good prediction.
Well, prediction actually one of the worst one to think about from the model, because it doesn't do a good job. Model has,
Best fit modeling. And then
well, there is a multiple purpose. It's some of the things that they are mentioning is, of course, you know, forecasting. You know, the reason you do modeling is because something you don't know about. That's the reason you do it. If you know from the data, you will not do modeling. You will take information directly from the data. The reason you are doing modeling is you are given a situation, you are capturing it with the models and using that information to answer something else which you don't know. That's the whole idea. It could be future in time, it could be different population. For example, they have studied the behavior of drugs, certain drug for the disease in India, but they don't know what happened in US. So you are using a model for that drug and applying it in US. So taking same time, it's not future time that I'm talking about, but same time, different population. Sometimes we don't know what is the mechanism in which the certain ecological factors are impacting the spread of, why is the disease spreading in this population? I want to know, there are 10 factors, I want to rank them. Number 1, is this one very important? See, most of the public policies are lacks money. Or in fact, there's no organization with infinite amount of money except Bill and Melinda Gates Foundation. That's a different issue. But most of organizations lack resources or limited resources. So you have to distribute those resources into factors which are key as factors, right? So what is modeling doing is listing out the ranking of the factors. Number 1, this is the key factor. This is the less important factor. This is the least important factor. Does that make sense? That's the purpose of the modeling. So actually most of the time this is what it is used for. Not for prediction, not for other population. It is used for understanding which factors we can rank it number 1 these ways. All these modeling studies are doing that. Okay. Sometimes we don't know, for example, during COVID, we didn't know how many cases are getting infected in Uttarakhand, in Uttar Pradesh, in Delhi. Different types of population, different type of weather condition, different type of pathogens transmission processes. So how will I know? So we were estimating the production number for UP, Uttarakhand, separately. And that was giving, it was very fast in Delhi because of factors local to Delhi. And those factors we were listing out. Same thing in UP, same thing in Uttarakhand. It will not be same thing that we studied it in Uttarakhand and it will be in whole India, it will work like that. It will not work like that. So what I'm trying to help you guys with is ask your questions in, it could be very crude question, which is fine. But when you start having discussion, then you realize that there is other aspects that we are not really pondering upon. Okay, so what I will do is I will let her continue and then ask your questions. It is not that simple that, also don't, as I was started the first day, when I was in graduate school, I also had the similar things. What I thought was, oh, this is biology. Why should I listen completely in terms of, this is not my area. But when you start listening to these biologists or to statisticians, your mind try to understand their thinking process. It's very different. As I was saying, the word model in engineering is a toy caricature of some building, for example. Whereas in the social science, it is a flow chart. It's a language is very different. Same word, very different understanding. Mathematics, it's equations, right? Biology is a rat, mouse. So I think we need to understand this language of the field if we want to work in an interdisciplinary area. Otherwise, we are not justifying our research properly. And so that's why I'm saying, statistics, we need to understand what language she's trying to explain it to us. So help us make it more interactive and discussion oriented rather than as a lecture and listening it. Okay? So, okay. So Dr. Ghosh, floor is all yours. So continue please.
Yeah. Thank you, Dr. Moy, for your nice explanation about uncertainty and EDA. I'll continue with some common issues that can affect the exploratory data analysis in EDA. So first of all, there is if the limited data resolution. What it means? Means limited data resolution happens when the data is too aggregated or incomplete or imprecise to reveal detailed pattern. Why it's problem? Because EDA relies on patterns, trends and variability. If the data lacks details, important information can be hidden. Let's give an example. Like time resolution, data recorded monthly instead of daily. So it can hide the short-term spikes or drops. Another example is like measurement precision. This is one of the most important in different fields like nutritional science or any epidemiological field, like the measurement of age or age group, the co-founder. Age group may be taken as 0 to 18, 19 to 35, 36 to 30 instead of the exact age. So it can be one of the main cause and it is included in limited data resolution. Maybe there is some rounding or truncation errors, that is value rounded to whole number, remove small but meaningful differences. So these types of error or these types of common issues can happen in EDA. Next one is one of the most important is strong assumptions in EDA. So what this strong assumption is? Strong assumption occur when you implicitly believe something about the data without solid evidence. Like already Dr. Mubai mentioned, like particular region. We know this disease was occurred previously in particular this region, but we don't have any idea about any other region have this disease or not. So this is the solid evidence. Is there any disease or is there any particular disease in this region or not? We do not. If we do not have any solid evidence, we just assume maybe this disease also can incline or decline particular this region. This also may be occurred, and this is one of the issue. So the common assumption, what are the common assumption? We just assume. First one is data is representative, assuming the data set reflects the whole population. But sometimes actually in real field it does not happen all the time. No missing data bias, assuming missing values are random, but sometimes it's not random. We for our easy calculation or easy interpretation, we just assuming the linearity, but it also does not happen all the time. Independent, assuming data points don't influence each other, like particular any disease like tuberculosis does not affect immune system or any other effect, or if we consider like different types of like malnutrition or any or in case of anemia, maybe it's mother anemia or any sanitation, or it does not affect the children's anemia, but anemia and mother's anemia and sanitation or wealth index may be correlated to each other. Stationary, assuming pattern don't change over time. It sometimes assumes that the pattern does not change over time, but it does not really occur in all cases. Let's give an example. Assuming survey responses represent everyone, even if only a small group responded. So maybe a particular a very small group, due to costing reason, we just collect the response from the small group and assuming the whole response may be same, but it can't be happen all the time. Treating correlation found in EDA as evidence of causation. Assuming normal distribution without testing or visual confirmation. It is generally happen, especially since many of the distribution for large population, we assume it's behave like normal distribution, but maybe it's not only the normal distribution. Impact on EDA means, so what is the impact of strong assumption? So it can mislead the interpretation, overconfidence in early findings, incorrect conclusion that affect later modeling or decisions. Why it's matter? It's matter to generate the hypothesis, not confirm them. Limited resolution or strong assumption can hide real world complexity. It can also like what the actual situation and what the calculation, like what can we interpret. So there is a big difference. Lead to biased insights, already Dr. Mubai mentioned what kind of bias. Affect the variability or later statistical or machine learning models. It can also the model and what we assume, our assumption may be wrong. So there are some techniques to reduce these issues, like multiple visualization. In statistics, there are lots of different types of graph interpolation, like histogram, box plot, or scatter plot, or we can interpret it in different graphs and we can see the pattern, like how it changes or what is the trend of it. Clearly state the assumption when presenting finding, and the one of the reduce these issues, check the data collection method and the tentative and the final conclusion. Next is correlated parameters. What it means? It means that correlated parameters or variables are the variables that show a statistical relationship with each other. Maybe they are correlated to each other. We need to check it out. When two or more predictors move together, they are not independent. Like give an example, advertising spent across different channels, or temperature or energy usage, height, weight. This is the basic idea of common. Very simple example is height, weight. Of course, height and weight are correlated to each other. So why it matters in EDA? EDA often reveals
Dr. Ghosh,
Yeah.
is
Yeah,
your slide
sure.
moving? What we are seeing right now is your, this is the camera, right?
Yeah, it's just the second point. It's correlated parameter, the third one,
Okay.
the third ball actually, blue
The
ball.
correct slide. Okay, fine.
Yeah. And based on these issues caused by correlated parameters, maybe they can correlate it to each other. It can misleading the interpretation. So in that case, consider this and this point. Next, last we can compare the model. The last point is, so what is the purpose of the model? Model comparison helps decide which model explain the data best while avoiding unnecessary complexity, especially the important when predictors are correlated or we have any strong assumption or limited data resolution. So in statistics and mechanistic model, here are some points we discussed with uncertainty matters in public health. Now this is the all possible details. First one is parameter estimation versus calibration. So what is parameter estimation? Parameter estimation basically use data to statistically estimate model parameter with uncertainty. So we guess about, or in statistical language, the guess term is denoted as estimate. We estimate the model parameter. Whereas the calibration is adjust parameters so the model output matches observed data patterns. So here is the basic difference between parameter estimation and calibration. Next one is statistical and mechanistic uncertainty. In statistical uncertainty, what happens comes to the limited or noisy data. But in mechanistic uncertainty, it comes from assumption that I already mentioned in my previous slide. Come from assumption in the model structure. Next one is different parameter and similar curves. Different parameter values can produce very similar epidemic curves, but a good fit does not guarantee correct mechanism. If your model or your curve may be good fitted, but it does not imply or does not guarantee its correct mechanism. Why sensitivity analysis is essential in this field? Like it can check how result change when the parameter vary. Maybe the parameter vary. Maybe we can add or subtract any parameter. So how it vary, how it affect to the result, how result changes. Identify which parameters strongly influence outcome and improves the confidence in conclusion. Like sensitivity analysis is one of the most important cases where we can measure the result changes due to the varying the parameter or identifying which parameter actually the effect, that means the potential parameter, and improve the confidence in conclusion, like you can conclude uh, what is important and which parameter we can add or we can subtract, or we can, in that case, if we consider the right or potential parameter, we can conclude exactly what happens in the real situation. This is some R code actually. This is actually R. What is R? R is an software generally used in statistics and in different fields. But R is very easy and it is free software, so anyone can use it, and no need to remember the what is the code. You can easily give an access of R, and you can easily remember the code from website or any website. Like here as an example, this is the plot. First one, plot means the x-axis is based on, first one is based on time, that is put on x-axis, and second one is case, so the case over the time. Next one is if there is any needed like filter, if there is missing data or anything not applicable data, so we can replicate the data with like not available or any missing. So in that cases we just easily interpreted by the R code. And last one is this is a simple generalized linear model. The code is GLM. We can easily get from the net. So here this is just an example. Infected means infected people. That varies. Infected, this is Y. Varies x1 plus x2, where x1 is age and x2 is any kind of exposure. So we consider it the family as binomial. Maybe it's binomial, maybe it's quasi-binomial. Depends on your assumption and what your analysis, what do you want from your research. So this is the code. Code supports understanding, not blind fitting. So if we fit different types of model, we can also use different types of comparison, like which model fitted well. So this is simple R code. We can easily compare, or we have already mentioned that the graphical visualization. We can easily just input the data into R, and the appropriate code can provide the visualization of the graph, and we can easily interpret it from that. Is it normal or not non-normal, or is inclined or declined, or any outliers? We can easily interpret it. So these are the whole basic about the statistics method, about the uncertainty, why we use it, how should we use it in data, what challenges we face, and that's all. Thank you, everyone.
Thank you. Thank you, Dr. Bush. This was very helpful, and I'm not sure if you can see the audience. You can now.
Yeah, I can see the audience.
Yeah, so there are a few questions, if it is okay with you.
Yeah, sure.
Please.
Dr. Ghosh,
Yeah.
actually you talk about the strong assumption by doing the data modeling. Like you talked about normality condition. So what do you suggest? Suppose I have a data, especially in disease modeling, I'm not sure what is the pattern and what should be done with the data. So should I check the normality first? Some tests should I apply, because you're talking about the linear regression model, you're talking about parameter estimation. All these are based on the concept of normality. What I understood. So should we check first
Right.
whether data is normal or not, and then we proceed further? And if data is not
Actually,
normal, then
it's
how do we do these parameter estimation?
okay. So actually, in research paper, actually the parameter we can choose the parameter from the literature review, and also in fitting model, actually it's better to. I have already mentioned that it is a good question. So how we choose the model or what we do with the data. So first we is there any visualization of the any graph pattern, you can visualize it's normal or not. It is very easy. And for choosing the model you need to do what is the research question. You want to calculate the prevalence or any incidence or any exposure which are like influence the disease or anything else. So it depends on your research question. What is the research question? So what we what you want to conclude. So based on this, we fit the model. So the model actually from data then model, not model then data.
Also, I
So
want
is it clear?
yeah, I want to add a few things. We are
Yeah, sure.
loosely using word model here. We are trying. Let me just explain very clearly. There is a deterministic mathematical model, and then you need an estimates of the parameters like transmission rate, recovery rate, all those things. Then you build statistical models connecting data to obtain an estimate of this transmission rates, let's say. So this is two different models we are talking about. Always whenever we deal with a data set, you generate a statistical model. The mathematical model is there already. Eventually the outcome of the statistical model will go as an input to the mathematical model. Does that make sense? So for example, transmission rate, recovery rate, for example. How do you obtain a recovery rate? How do you obtain a recovery rate? Which data is needed if I want to know what is the rate at which population people are recovering from a particular disease? What data do I need? Record people of what? Yeah, we will ask the people or we will follow up that infected people for the duration, right? Duration of infectionness. Usually it is done in two ways. If it is a disease that is not needed hospitalization, even if it is needed hospitalization, people don't show up for hospitalization right the day they are getting infected. Usually it takes few days for them to show up for the symptoms, right? So if I want to know how long a person is infectious or infected, then there is two ways. You will ask a survey to a question. How long do you have for symptoms? The doctor asks this thing, right? And they note it down. And that is called as an electronic health record. That is what on the last day there will be a class on electronic medical record. And that information along with another survey which tracks, because person will show up today, right? They're showing symptoms. Already few days has elapsed. So there is a survey right that day when a person is entering the hospital, and then how many days a person remain in the hospital. So it's an addition of these two terms, two durations. That's the time a person is infected, right? And that time is a duration of infected. 1 over that, 1 divided by that duration is a rate of recovery for that disease, that population that we have. Now again, this is one person I'm talking about. You have to average it out over many populations, right? Many individuals in the population, right? So you have to think about when we are interested in, see, the actual, if you have a lot of data and you want to extract information from the data, then you test different type of exploratory data analysis. You do normalization, whether the data variables are normals or not. There are different type of analysis you do. But here the question is different. Here the question is, you want to estimate the parameters of the mathematical model and you are using indirect data. For example, transmission rate, as I said earlier, you cannot find it in the field. It's difficult to get it in the, because it requires contact rates. So how do you get it indirectly? How do you get indirectly? By taking the case count data, which is what Dr. Ghosh was talking about, count data, number of cases at different time points. That's a time series data, right? How is this is like this look like scatter plot. And so if I don't know the beta, which is the transmission rate, I give one value of beta, arbitrary value, and then I run the solution of this model and I see how closely it is fitting by taking residuals, right? And we find the residuals. So with that fixed value of beta, there is a certain residual we will get, sum of residuals we will get, right? That's an error. So if I change the beta, there will be a different error, right? So, and so on and so forth. So you will get a list of betas and a different errors, corresponding errors. You find the minimal error and that's corresponding beta is a good fit. And that's how you get. But when you do the fitting, you are using a statistical model in the middle. It's not done, the fitting is a model basically, statistical model. Fitting, fitting can be done in a multiple ways under different assumptions. Now assumption is about what? How the data is collected in the field, how the uncertainty is captured in the field. What data we are talking about? Time series data. Right? This data, how it was collected. That is what as a modeler, a statistical modeler has to think about. Mathematical model is done with the model. He's waiting for that estimate to come. You understand my point? So now the question is, you look at this time series data and you do lots of analysis on that. It could be, now it's over time, right? So you have to, it's a count data. I don't know if you have heard about Poisson process. So there's a theory behind it which is based on Poisson process, because it's a count data, counting data, and that's what you use it. And there is assumptions that goes how each of the data points is collected. What is the error for the data collection process made for collecting each of the data points in the time series. So what is the important thing is, how is the fitting model, the statistical fitting model, so there is a hidden statistical model which we don't see. We use these softwares and plug it and then we get it. But there is a statistical model and assumptions behind it. That is what we are fitting. You're not fitting the, the mathematical model is getting fit, but there is an intermediate mechanism that is working out as a statistical model. Okay, so that is where is the question is now. If you want to purely do statistical analysis, if I want to only analyze the time series data, it has nothing to do with the mathematical model. We will do a different type of analysis. Right? It's a data, and we want to understand how the cases are changing over time, and we look into statistical models separately. It has nothing to do with the mathematical model. But when we link this data to the mathematical model, there is another type of model which is a statistical model. So these are two different questions. When we ask normality and the data, how to look at the data, we are talking about this part, when you are looking purely statistical aspect and nothing to do with the mathematical model. Even though assumptions are important here also in the statistical model when you fit the mathematical model, but that's a different way of looking and this is a different way of looking. Two distinct things. Okay, does it help in clarifying?
But we are doing the parameter estimation. The estimation which we do, they are also based on the concept of normality. my data set is not normal, so then the estimation which I'll be getting, then maybe.
But how do you know your data set is not normal?
That's why I'm asking. That's why I'm asking.
Well, again, when you say data set, what do you mean by data set? That's what I was clarifying. You see, in mathematical model estimation, there are three types of different estimation. One, for example, recovery rate. Did you do any model? No, there was no model. You use the literature, look for average duration, and you pick that thing up, directly use it. That's a direct estimation from some other study. Second is you have, for example, raw data and you are averaging it in some sense, weighted average, and getting simple models and then using that thing to estimate your parameter, like adherence rate, for example. Adherence rate in the population, because adherence is to the drugs or to the treatment, to the interventions. Third type of is an indirect estimation, which is basically, as I was describing, the transmission rate is an indirect estimation. You don't have the direct data, you can't average it out something, so it is not possible to get directly from the literature. So you use indirectly time series data, which has nothing to do with the transmission rate, right? Time series is just showing the count of cases. Now in that there is a statistical models. So normality assumptions, you have to look at the time series. At each point is a randomly selected from the population. So each data point has a different assumptions. So there is a normality in each point, not as a one normal, because it's over time. So that's why you have to think about what is the assumption we are talking about here. It's each point that is coming from the data has its own distribution. You understand what I'm trying to say? So it's not a one distribution that we are talking about in time series data, it's many distribution. Okay, so there are different assumptions. Again, this is going deep into how we do data analysis before time series data is used in the model. So you want to add, Dr. Ghosh, something to it? Are you there?
Yeah, I'm here. Can you hear me?
Yes, we can hear you.
Yeah. This is your nice explanation. Is there any other question from the
Yeah,
students?
any other questions, guys? Okay, so that reminds me that I will show parameter estimation tomorrow. There will be class in which I will be talking about these things. So that way you will get a better idea of that. But any more issues, questions? How many of you have used a statistical model, any of the statistical model? Yep. And you used it to do what?
Rental estimation in Delhi. We had a data from Kaggle, and we did, it is a project, it was a project of the data mining code. So this data, so we first conducted the exploratory data. We get some clues there, like location matches location and its distance from important landmarks. And some clusters, so we got some clusters which are dominated.
So you had a data.
Data and EDA, we conducted EDA, then we tried to make a model for prediction of the rate at any place in Delhi. We tried, it was not present, but we tried. In that we tried the models like linear regression, then logistic and ridge regression, not logistic, ridge and lasso. These are the regression models, and they not performed very well on the data. Then we moved to ensemble model, decision tree, random forest, and another one ensemble model. So random forest was the good for that.
So these are all statistical model that he is talking about. So yeah. So again, for that you need a whole lot of data. right? And in disease models, you don't have typically the data, and that is very challenging. So anyway, so I think Dr. Ghosh, thank you very much. Let's give a round of applause to Dr. Ghosh. Thank you very much, Dr. Ghosh, and hope to see you soon.
Yeah, see you soon. Merry Christmas to everyone. And in the last question, I just need to mention, maybe there is some advanced AI techniques like you mentioned random forest and support vector machine, etc. You can try the cluster analysis if you are interested. This is maybe fuzzy clustering, one of the paper already published. You can use, you can search on net, it's fuzzy clustering. This is based on fuzzy and clustering, that's based on the cluster data. If the data is clustered, you can use it. This is my suggestion. You can try the model. Okay. Thank you. Thank you again, everyone, and Merry Christmas. Have a good day.
Thank you very much. The next thing is we are going for lunch, right? Ashwini, how much time lunch we have?
1 minute.
So no, but how much long break we are taking for lunch? 1 hour? 1 hour is okay? So it's 1 o'clock right now? 1 o'clock, so let's meet at 2:15. Let's meet at 2:15, and when we come back, there will be a topic on AI tools that we are using for disease modeling. So we will discuss on that with Dr. Namika, and then after that, I will go over something in R, simulations in R, and then finally we will discuss almost 1 hour of your projects. I hope today the project is completed, right, for all of you guys. So that's the plan for the afternoon, and hope to see you guys in 1.5 hours, 1 hour 15 minutes. Thank you.